This is the walkthrough video for PCTC 2023, question 11, huddles, round 2. Okay, so this question is quite like Conway's game of life. It's where we're given this initial state, which is what our input is, and then we're told to simulate a set of rules until nothing changes, and then we have to calculate the Manhattan distance and print that out. Okay, so um, I guess the key with this question is trying to figure out like an efficient way to write this and do the data representation and all of that stuff, because the logic of this problem is not too difficult, and you can probably pretty easily write yourself a program that's like 200 lines long, but it's going to take you a while. So we're going to try and figure out a more efficient way to write this. And there are also a few bits where you can easily trip up as well, especially if you've never come across a question like this before. Then there are definitely a few bits you can trip up on. Okay, so let's do the easy bit, which is taking in our inputs. So let's just have a list called sheep, and as many times as our first input, let's input that many sheep. So let's take in our input, and let's append that to our variable, our list called sheep. And what we should actually do is append the eval of it. So what we're doing is by applying eval or evaluate to our input, is we're converting our input, which is currently just like a string with a number, comma, and then another number. We're converting that into a tuple of an actual number as opposed to a string. And so now if I were to print out sheep, we now get a format that is more usable, as opposed to just having a load of strings. We now get a usable format. And this is just like a good life hack in Python if you ever want to save yourself some time by not having to bother processing the input as much. And yeah, here you go. We just have a list of tuples, but each tuple is effectively what we inputted. Okay, so we've done that. Now for the hard bit, the part where we have to actually simulate this game. So this game is going to run an infinite amount of times until we reach a certain point. So this is where we're going to use an infinite while loop. And every time we run the while loop, what do we do? So that's a good question. Let's do nothing for now. Let's go through for every I don't know, let's call it thing. For every thing in sheep, the issue is that sheep is both the plural and the singular term, so I can't say for every sheep in sheeps. So anyway, for every thing in sheep, I want to calculate what the theoretical next position of that sheep is going to be, of that thing, by following these rules, which is that you always move one closer to the origin. And if you're on the axis, you just move one in the axis that you're not on. And if you're not on the axis, you move diagonally to the origin. If you're already at the origin, you kind of stay there. So how do we do that? So just a reminder, thing at this point is just a tuple of the coordinates, for example, 4, 2. And we want to make them closer to the origin. So let's assume, for example, our coordinates are 0 and 5. What we want to do is quite obviously make this into 0 and 4, because that's one closer to the origin. And how would we achieve that? Well, we're just minusing 1 off the coordinates, right? So it's almost like we're doing thing 1 minus 1. But the issue is, what if, for example, this was minus 5? Well, then to get closer, to get 1 unit closer to the origin, we need to do a plus 1 to get to minus 4. And so to account for this idea, we need to basically figure out whether we're below or above, whether we're in the negative or the positive, and that determines whether we add 1 or we take away 1. And so what we can do to figure out whether it's positive or negative is just essentially divide the thing by itself. So if we divide, for example, the y coordinate, you know what, let's make this a bit more obvious. So let's say the x coordinate and the y coordinates are going to be thing. So what we're doing here is we're just unpacking thing. That's the term, unpacking. And so, for example, x would be equal to 0 in this case, and y would be equal to minus 5. Okay, and that just means we can have cleaner variable names down here. So let's change this to y. And so what this line of code does, or what this in brackets does, is we're just dividing the thing by itself, right? And that turns it into 1. Like the answer to that is always 1. Like minus 5 divided by minus 5 is 1. 10 divided by 10 is 1. And that doesn't help us. But what does help us is if, for example, we do the absolute value here. So if we're dividing something by the absolute value of itself, then we get the sign of the actual thing. For example, 5 divided by 5 is 1. That's positive. 5 is positive. That's fine. Minus 5 divided by the absolute value of minus 5, which is just the positive value, so 5. So minus 5 divided by 5 is equal to minus 1. And so minus 1 is negative and minus 5 is negative. So this statement is kind of a way of trying to figure out whether we have a negative or whether we have a positive number. Because you divide the number by the positive value of itself, and therefore you can determine whether the result is negative or positive, leading to whether your actual number is negative or positive. Okay, so in the case that it's positive, then our original number is positive, for example, 5, and we want to decrease that by 1. And so this will work, right? Because this is just like saying y minus 1. And if y is negative, say y is minus 5, then we want to add 1 to get to minus 4, for example. And how do we add 1? Well, we already do that, right? Because this value is going to be minus 1, because that's minus 5 divided by 5, which is minus 1. So we're doing y minus minus 1, which is just equal to y plus 1. So this is like, hopefully that made sense, but this is quite like a nifty trick to essentially calculate the step that you need to move closer, whilst also accounting for both positive and negative directions. Of course, you can like bother writing more if statements to kind of solve this and look for each case. But once you get good at like trying to spot these tricks, then it's way faster to code. And we can basically just do the same thing but for the x coordinates. So let's do x minus x divided by abs x. And let's convert that into a tuple. And so our new position is going to be equal to this tuple, where this is the x coordinate and this is the y coordinate. But if you're particularly observant, you may have noticed that this might actually be equal to 0, right? Because if our coordinate is 0, then we're doing 0 minus 0 divided by 0. And you can't divide by 0. Python would give us an error if we divide by 0. And so what we should do instead is to make sure this is never 0. And again, in this case, you could, again, add even more if statements. But another neat way of doing this is to use max. And so I'm selecting the maximum of 1 and the absolute value of our coordinates, right? So instead of just dividing by the absolute value of the coordinate itself, which might be 0, I'm saying I'm going to divide by the maximum of either 0 or 1. So the benefit of that is that it means that it essentially removes the 0 case, right? Because if 0 ever happens, we're just going to replace the 0 with a 1, and therefore Python won't throw us an error because we're not dividing by 0, we're dividing by 1. And we know this will still work because x is still going to be equal to 0. So this entire expression is still going to be equal to 0 because we're still doing 0 over 1, and that's equal to 0. And that's good because if we're at the origin, we don't want to move. So we know this will still work. And all we've really done is just made sure that Python doesn't give us an error. We haven't actually like done any real coding. It's just making sure Python doesn't give us the error. Okay, so that is actually all we need to calculate the new position of each sheep. And so this is obviously like a pretty long and complicated line of code, especially with all of that maths. But it's the line of code that does all of it for us, right? We don't have to bother with a load of if statements. Okay, and now this is the harder bit. So we've calculated the theoretical new position of each sheep, but as we're told above, the sheep doesn't necessarily move to that position, right? Because if two sheep want to move to the same position, we're told that that's not allowed. Or if a sheep moves to a position where a sheep was there beforehand, that sheep also can't move there. So we need to figure that out, and that's going to be the difficult part. So what we should do is we should pre-calculate the new position of every sheep, and then check to see if multiple sheep want to go to that position. Because we can't check to see that as we calculate this, right? As we go through this for loop, we're discovering new information, right? So we can't do anything without risking ignoring useful information. For example, say I had a sheep C, and say sheep C wants to go to coordinate 1, 3. And let's say, oh yeah, no other sheep's there, let's go. But then later on we have, say, sheep F, and sheep F also wants to go to coordinate 1, 3. Well, the problem is sheep C has already gone there, and that means that because sheep F also wants to go there, neither sheep C nor sheep F are allowed to go there. And so we've made the mistake by allowing sheep C to go there. So that's like the problem highlighted about why we need to pre-calculate all of these values. Because everything in this problem, or everything in this question, it happens simultaneously, all at once. And so we need to make sure that we have everything pre-calculated ready to go before we actually do anything. And so we're going to kind of leave that for loop as it is. But of course, we actually need to like store the new somewhere, the new coordinate somewhere. Um, and so let's store it in a dictionary. So uh, new coords. Let's call it, yeah, let's just call it new coords. It's gonna be a dictionary. And what we actually want to do is we want to use this thing called default dict, which we're importing from collections. And what default dict does, as a quick overview, if you don't know it, is instead of creating a normal dictionary like this, if you create a dictionary like this, default dict, and then you put, say, list in those brackets, it's basically going to say whenever you call something in default, whenever you call something in this dictionary, and if it doesn't exist, so if that key that you're calling doesn't exist, it's going to automatically create it for you and sets the default value to an empty list. If I want the default value to be an empty integer, I'll do that, or an empty string, I'll do that, and so on. So this is really just a way of being lazy again, right? We're just saying that if the thing I want to reference does not already exist in the dictionary, just create it and make it just reset it to an empty list if it doesn't exist. And the reason we're doing that is because down here on line 15, we're gonna add something to new chords. So we're gonna take in new chords new, and we're gonna append thing. This might seem a bit confusing. So let's actually just print new chords, and then we'll just break out to that so it's not infinitely run. And then we'll see what's actually outputted here. Right, so we're given this dictionary, which is essentially this bit. You can ignore everything up to that. That's just telling us that it's a default dict. So we're given this dictionary, and the key for each thing in the dictionary, for each item in the dictionary, the key is the value of the new coordinate. So for example, 0, 1, or 3, 1, or 3, 0. And then the value of that key is a list containing each of the old coordinates that map to it. So essentially, this dictionary is telling us for every new coordinate that we want to go to, what are all of the current coordinate sheep that want to go to that. And that means that we can check whether multiple sheep want to go to this given new coordinate. If multiple sheep want to go to, say, coordinate 3 and 1, then this list is going to have multiple items in it. And therefore, we know that none of those sheep are allowed to move because of the rules of the game. But in this case, for example, there's just one item in that list, and therefore only one sheep wants to move to this coordinate, and therefore it probably can move to that coordinate. And of course, you may have also noticed that all of these are floats. We only want to deal with integers. It doesn't really matter whether they're floats or integers for now, but just to maintain consistency, let's just keep them integers. And so let's just do an integer division up here on line 14 instead of the normal division. Okay, so now you understand what new chords is and that default what default dict does. And actually, let's just demonstrate what I do if what happens if default dict isn't used here, because it means that on line 15 we're calling or we're referencing this key that doesn't already exist in the dictionary, and so it's going to throw us an error. Show outputs. Yeah, it says key error 01. So it's basically saying that this key doesn't exist, and yet we're assuming it does. And we obviously can't assume it exists if it doesn't exist. But by using default dict, we can assume it exists, because if it doesn't exist, it creates it for us. Okay, so now let's actually go through every new coordinate and check whether the sheep is allowed to move to that new coordinate. And we should also probably keep track of our brand new sheep grid. So let's say new grid is going to be equal to nothing. Or actually, yeah, let's call it new sheep. So all of our sheep, we're going to add their new coordinate to this list as we figure out what it is. And so let's go for coord in new coords. We want to go through the items. So we want to go through for new coord and old coords in new coords.items. Okay, so what we're doing here is we're going through the dictionary, and we're just going through the key and the value pairs, and we're calling the key new coord and the value old coords, because that's just the list of all of the old coords that map to the new coordinate. Okay, And now time to do the checks itself. Time to check if the sheep is allowed to move to that new coordinate. And it is allowed if the length of all coordinates is 1, right? Because if only one sheep wants to move to a new coordinate, then it's allowed. But also, as we're told earlier, somewhere up here in this really long description, we're told that okay, I don't know where it says that, but somewhere it says that basically if the new coordinate on the previous turn had a sheep on it, you're not allowed to move to it. So we need to make sure to check whether new coordinate had a sheep on it. And just well, to do that, we can just say, and if new coord is in our sheep list, this list. So basically, actually it's not in. So let's just add a not out here. So basically what we're doing is we're checking both checks to make sure whether it's a valid move for a sheep to move to this new coordinate. And we know it's a valid move if only one sheep wants to move and if that new coordinate doesn't exist in our current grid, which is represented by the list called sheep. And if that is the case, then to new sheep, which is our list of all of the new coordinates of where the sheep now are going to be for the next turn, let's append the new coord value because we figured out that it's a valid value to go to. And if it's not a valid value to go to, well then to new sheep, we're just going to append basically everything in old coords, but you can't just append a list to a list. But what you can do is you can add a list to a list. So let's add the list to the list. So essentially what we're doing here is old coords is a list of every old coordinate that would map to new coordinate. And this line of code, this else statement, is only run if the old coordinates are not allowed to go to the new coordinate. And therefore the old coordinates remain in our grid. And so we're just going to add those old coordinates to our brand new new sheep list. Right, so by the end of all of this code, we now have a list called new sheep, which represents the next grid. So the current grid is called sheep, the next grid is called new sheep at this point in time. And now all we have to do is we have to update it, right? We have to say sheep is now equal to new sheep, right? Because all we're doing is we're just updating it. But in Python, you can't just say one list is equal to another list. For loads of complicated reasons, if you want to search this up, it's called mutable, this concept of whether something is mutable or not. But you don't need to worry about that. But what you do need to know is that you cannot just like say one list is equal to another list. If you do want to say that, you have to add .copy at the end. So we're saying the sheep list is now going to be equal to a copied version of the new sheep list. And we should also do something before that. We should check if the huddle has occurred. And the huddle occurs when the sheep stop moving. And so we know the sheep stop moving if the current grid is equal to the new grid that we just calculated. So if our new grid has no different coordinates to our current grid, then we know all the sheep are still in the same place, and therefore we're done. We found the huddle, and therefore we can print out the Manhattan distance. But before we do that, let's just discuss why we've done it this way, right? Because it seems like it's a bit of a long-winded way to achieve this, it may seem. Like, why are we having multiple for loops and multiple lists? And the reason we're doing that is because everything in this scenario happens simultaneously, it happens all at once, right? So we're not updating one sheep at a time, we're updating every sheep at once. And that means we have to, as we said earlier, we have to do all of the pre-calculations to figure out what the situation actually is and what it's going to be. And then we have to do even more calculations where we actually do the sheep moving. So we have to almost separate the calculations and the predictions to the moving of the sheep themselves. And the reason we have to have two new lists is so that we can actually check whether any of the sheep have moved. Because we know if the sheep haven't moved, then we've reached the huddle. And another point as well is that you see here on line 20, the condition to check whether a sheep is currently at the new coordinate. That's only possible if we store the current grid as well as the new grid that we're building up. Whereas if we were just to modify our current grid, then we would be changing the information as we're using the information, which is not good because we want to do this simultaneously, right? We're given all of the information at once as a block, then we need to calculate what the new information is and apply that and repeat that same process again and again. And I think it does kind of try to make this a bit more explicit somewhere here. It says all sheep movements occur exactly at the same time. And so the sheep's current position that should be used to decide if the next movement is possible before any other positions have been updated. That's the key bit. Before anything's been updated, we're using what we currently have to calculate stuff. And that's why this order of our code is a bit funky and it seems like we've written a bit too much code than we need to. But if you've ever coded like Conway's Game of Life or a variation of this problem before, then you know, like you've probably seen code similar to this because it's a very similar line of reasoning in terms of how Conway's Game of Life works. Okay, so we've done that, and now we have to print off the final thing, which is the Manhattan distance. And the Manhattan distance is just the distance of each coordinate to the origin. And that's actually pretty easy in this case, right? Because we're already given the coordinates in coordinate format. And so we can just calculate, I don't know how to spell Manhattan, let's just do distance. Let's say distance is equal to 0, total distance is equal to 0. And we're going to go for every coord in sheep. And we're going to say total distance is going to be itself plus equal to the x coordinates. But we need to make sure it's a positive x coordinate, right? Because the Manhattan distance only counts for how far something is from the origin. The Manhattan distance doesn't care like which direction it is from the origin, just how far it is away from the origin. And so let's absolute the number to make sure it's positive. And then we can repeat the same line of code but for the y coordinates. And just like that, we should have our answer. And let's submit that. So again, all we're doing here is we're just going through every coordinate of our finalized huddled sheep grid, and we're adding the value of that coordinate to our total distance. And that works.